stationarity, that's why we ended last time. Two types, strict sense and weak sense. Problem with strict sense stationarity is if you have a lot of time points, the joint PDF at different time points must be independent of each other. You've got to derive the joint distribution. It is painful. So we simply check for WSS and what are the conditions. W stands for either weak or wide. Conditions.
The expectation of the mu is constant for all t.
Expectation of the series is constant for all t. That is our level. This is something we have seen since day one. I've kept drawing that red line, blue line, going through some level. And the second condition is the most important of the two, which is the covariance of xt, xt plus h, which we denote as gamma sub h, must be independent of time, must be independent of time. In other words, it should only depend on h. So, yes.
What was the name of that notation? Of the magic
But right.
Which one?
But right. This function.
No, just the name of that notation.
This one? Yeah. It is the autocovariance function for lag h.
But what's the name of the sign?
Oh, the sign.
Yeah.
Gamma.
Gamma. Okay.
So gamma sub h is the autocovariance function. ACVF standard notation. What is rho h? Writing all these because we will be seeing these quite often.
Correlation.
Coefficient.
Correlation
Function. Autocorrelation function. Drop the V, we simply have ACF. The range of autocovariance is from -infinity all the way up to infinity. What about the autocorrelation function?
-1 to 1.
-1 to 1. How do we write rho h in terms of gamma h? If you go back and look in your notes, the autocorrelation function
Is it like covariance of xt plus h over square root of variance xt times the variance of xt plus h?
very good. The square root part is simply the standard deviation. The square root of variance is standard deviation. So here is something, it is a good point to introduce this. We know xt is the series. Your book uses z sub t for the actual series, and z tilde sub t for the centered series if you subtract the mean out and if it is 0. I'm just going to call it xt because that is convention. As an example, no, sorry.
Got one right here.
Okay. Phi is sine. Phi is we'll keep sine here. Of course, there is sine naught, but doesn't matter for now. Plus 18. Going back to Thursday, I've got lecture in 80 seconds. We talked about a sub t, which is also epsilon sub t, right? I'm sticking with a because it's easier. We already have a lot of Greek going on. What is a sub t? Noise. And what is our condition for a sub t?
Identically distributed independence.
Very good. Independent, identically distributed with some fixed distribution, typically normal. We want the mean of a sub t to be 0. In other words, the theoretical value of a sub t, the mean of a sub t has to be 0, which is why I'm using expectation. And the variance of a sub t is sigma squared sub a. If it is a white noise process, this value would be 1, typically close to 1, and the distribution would be Gaussian or normal. If mean of a sub t is not 0, it's not a big deal. That mean will get added to mu, which when we subtract, it's going to be centered at 0. So typically 0, but it could be not 0. Okay. If that is true, I'm going to argue that is also true for all h. Having said expectation of this random variable to be 0, variance of the same random variable to be equal to sigma squared a, I'm going to argue that covariance of AT, comma AT plus h is equal to sigma squared a for all values of h. Under that condition.
That sounds right to me because of the variance. AT. Yeah, so it's like in the denominator that's one.
So you're fixing it to be a constant, but logically, why do you think that this is true? I'm saying no matter what lamp you look at, in other words, 80, comma 80 minus 1, 80, comma, 80 minus 2, they will all have the same variability of sigma squared A. The answer is right here. Cayman actually gave me the answer. I feel like a part of me is missing because I don't have my coffee cup.
Because it's identically distributed.
Very good. It is independent, one, identically distributed. So no matter what time point you pick, whatever applies for h equals 0 will be the same for other cases, which is why it is a constant. Now, there are processes where it's not this simple. In other words, we would have some value. I'll show you when I write it in matrix form. So why is this true? Why can I say that covariance of 80, 80 minus 1, 80 minus 2, all be the same? It's because they are independent, identically distributed. Good. That said, do you agree? Well, can I erase this part? Yes.
So I learned in probability and statistics that for two independent random variables, the covariance should be 0. Because you can break up the e of x, y, and the e of x times, or e of the expected value of the two variables. You can break them up when they're independent, so that the whole covariance term would go to 0. So why is that not true here if they're independent?
Great question. So, independent and identically distributed simply means first the distribution is the same throughout, no matter what time you pick. Yes? The independent part, I'm saying that whatever that happens at time t is independent of whatever that is going to happen at time t plus h. What I'm referring to here is the variability of 80 and 80 plus h. So you are correct to say that this will be 0, but what I'm arguing is 80, 80 plus h, and you take the covariance, it's no different than the variance. Right? It is just the variance at every line that you think of. Do you agree that a random variable has variance? How 80 varies with 80 minus 1 is the same as how 80 varies with itself. How 80 varies with respect to 80 minus 1 as variance is the same as variance 80. Good? So all I'm saying is this is equal to variance of 80. So that is h is equal to 0. When I write it in matrix form, you will see what I mean. Okay, before I get to simplifying this, I am going to find the variance of, well, let's start with the expectation of the series x2. I started with something simple right here so that you can understand the theory behind it. Whatever we have here could be applied to our entire ARB series, MAQ series, RM series, doesn't matter. So, for that simple case that we have, psi xt minus 1 plus 80. Good. Which, if you distribute, because expectation, you can simply distribute values or distribute the expectation, you'd end up having psi 1 xt minus 1. Agreed. And then you would have expectation of 80. But I know what expectation of 80 is, correct? That is simply 0. The bigger question now is what is expectation of psi 1 xt minus 1? The series is random because of that part. Without that, all you're saying is xt is some multiple of xt minus 1. If it is an AR2, xt is some multiple of xt minus 1 plus some multiple of xt minus 2. Pretty much, it's an average, correct? The moment you put AT in there, it becomes random. That said, what is the expectation here? Well, let's start with a hint. We can take psi 1 out. So go ahead. Okay.
This is just the sum of our
Okay, let me ask you this question. Do you believe xt minus 1 as is, as a number, is random? No, it's not. If you put xt minus 1 here, you'd have psi 1, xt minus 2, plus 80 minus 1. Again, you'd come to this step. So, in a way, that is a measured value, which is a constant. So, overall, this expectation would be some constant. Do you agree? So, this is some constant. In this case, psi 1. Times whatever this would be, and I don't want to give it a value, I'll just call it constant because we can go in a very recursive fashion here. Okay, did we write the next 2 lines? Yes, going to erase this. And don't get spooked by chapter 2 in the textbook, it is pretty intense. A lot of stuff, they are intense. I'm picking and choosing, so just focus on reading assignments. Okay. Extend the same idea. Going to go for covariance, xt, comma, xt plus h. Good. Covariance of psi 1 xt minus 1 plus at, psi 1 xt minus 1 plus h plus at plus h. Do you see what I did there? So the first part is for xt, the second part, t plus h, so t, I simply wrote it as t plus h. Good. Okay. Those who took 3162. How to write this? Well, hopefully it comes back to you. If I have x plus y, u plus v, side note, I really don't want to throw in a whole bunch of constants, so I'll keep it simple. This would equal to the covariance of x comma u plus the covariance of x comma v plus the covariance of y comma u plus the covariance of y comma v. Is it coming back to that? So x comma u, x comma v, y comma u, y comma v. I could use the same logic over here and distribute to get the covariance. So first part, covariance of psi 1 xt minus 1 is. If you can't visualize it, let's put a box here, call that x, y, u, v, associate with the formula that I just wrote. It's on bottom left. So x, u, so psi 1. Xt minus 1 plus h, xv, covariance psi 1 xt minus 1, comma, a sub t plus h, plus covariance at, comma, psi 1 xt minus 1 plus h. Covariance is the last part, at, comma, at plus h. Good. So x, u, x, v, y, u, y, v. Earlier I mentioned I don't want to throw in more constants in this expression. If you Google this property, or if you did property of covariances, probably see a times x plus b times y, c times u plus d times v, and then you can manipulate the constants also. Size are the constants here, but my explanation is simply going to be logical without getting into the math part of things. Good? Okay. That and that, both of them are they random. Not random. What? We have it at least not random. And not random. So random, only random variables have expectations, variances, covariances. So that is meaningless. So that's going to be 0. Agreed. Okay. How about the next one? Do you believe that a measurement at time point t minus 1 would have anything to do with some random stuff happening at time t plus h? This is where independence comes into play. So this is just some fixed value. That is a random component. You split them up, that would be 0. Mind you, I'm simplifying the explanation so you don't get confused. In a recursive manner, xt minus 1, xt minus 2, they're all random, right? Reason being, each time you do that recursion, AT will keep popping up. But I don't want to get into too much detail because I want to illustrate a simple point. So 0, 0, what about the next term? Random component at time t, measurement at time t minus 1 plus h. Do you believe that they would have a connection of some sort? No. So that would go away. The last part, at plus h. Noise. What do we expect again? Variance of A. Again, I'm not saying that this value is not 0. I'm just suggesting because of the way we define this variance, no matter what time point you pick, you will end up having the same variance. Good. So in that recursion, go time and time again backwards. So from xt goes to xt minus 1, xt minus 2. There would come a point that where these two values will match up, right? For instance, here h must be equal to 0, correct? You do one other recursion, it will happen at h equals negative 1. One more recursion over here, that will happen at h equals minus 2, and so forth. So the simple point I'm trying to illustrate is this value would equal to sigma squared A under one condition when h equals 0. Good? First thing. You can put h equals 0 here also. You don't want to get confused. I think that's where Omar's confusion came from. Put it this way. Let takes a trouble.
You have for all h underneath it, but then when h.
I'll take it away.
Okay.
Yeah, I'll take it away. I don't want to confuse. In a more general sense, covariance of a sub t minus I, t minus j equals sigma squared A when I equals j. Good. I'll write it that way. This way we want to have any confusions. Under here, notice I specifically wrote it as I minus j. You are going to get used to this. It will pop up time and time again when I do some algebra. I minus j is going to play a role significantly. So the noise at time I would equal to time j, resulting in the variance sigma squared A. Okay. If this is 0, then I would have variance of xt, square root of variance of xt. Denominator would simply be variance of xt. Do we agree? If h is 0. Numerator will simply be covariance of xt, comma xt. Good. So when h is 0, can I erase this part? Hayden, did you say something?
think it's 1, right?
It is 1. So when H is 0, rows of 0 would be covariance of xt, xt, which is the variance. Variance over variance, you end up getting 1. However, gamma at 0, which is the autocovariance at 0, is not 1. Thus, is simply the covariance of xt, xt. What is that value? Which is signified A. Okay. Why did we do this? I started with this part, or I wanted to get to this part, and extended to something bigger. There is. If life was that simple, I wouldn't be on this planet. I'll be in a different galaxy. But it just isn't. What do I mean by that? Well, I have an important restriction placed on my series, which is IID 80. So I want the variances to be the same at this time point. But in real life, that is not the case. Your book uses N, so I'm going to stick with N.
What is this Greek letter?
Uppercase gamma. So lowercase gamma is not uppercase gamma. So gammas are covariance, autocovariance, rows, autocorrelation. Good. Do we know matrices? Yes. Okay. So we know that gamma is dependent on lags, and what is important to us are the lags, and whatever happens to the covariances at those lags. So lag 0, 1, 2, 3, dot, 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 n minus 1. 0, 1, 2, 3, dot, 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 n minus 1. This would illustrate hallmarks point today about independence and 0. And which is why I changed it here from all h to h equals 0. Those two are the same, correct? If the times are the same, then what is covariance? It is simply the variance, correct? Okay, I can write it as sigma squared A, and this is what Omar asked me when I wrote it as covariance 80, 80 plus H. If they are independent, shouldn't they be 0? Well, they are 0, but that wasn't point that I was trying to make. When I put h equals 0, it made better sense, or it made. 0, 1, are the times the same? No, the noise would be independent. I'll have 0. 0, 2 times the same? No, independent. 0 times say, 0, 0, 0, all the way 0. What do we have over here? Sigma squared A,
0, 0.
all the way up to 0. You can tell me where sigma squared A is going to pop up again.
2, 2, 2,
2, 2, 3, 3. In other words, only diagonal elements, sigma squared A, sigma squared A, dot, 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 sigma squared A, 0, 0. Fully sparse matrix by all means, this is a diagonal. Good. Piece of it, if you have to take a guess, what is that? Okay, earlier I started with autocovariance. Where did I end up? Or what did I end up with? Autocorrelation. Autocovariance matrix. I'm going to end up with the autocorrelation matrix. Any thoughts as to what that is? In this case,
Diagonal elements are going to be 1.
the diagonal elements simply be 1, so 1, 1, 1, dot, 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 1, 0, 0. A simple identity matrix. Here, matrix algebra, sigma squared A comes out. You will have sigma squared A times R. With me. So I is the identity matrix. Sigma squared A is the identical variance that we consider for our noise, and this is what we have. You may ask me, well, why did we write this autocovariance matrix, autocorrelation matrix? Well, you can't do stuff in regression with multiple predictors without matrices. Do you agree? I believe Alberto, who's actually doing a course, matrices and data analysis. You cannot do data analysis without matrices. By all means, a table of data is a matrix, correct? Same thing, time series, you can't do anything without matrices. And what plays a significant role? AC via matrix, ACF matrix. I won't get into too much detail because I want to introduce theory, but not too much theory. So this matrix, both autocovariance and autocorrelation, will satisfy one condition. The right condition must be, well, let's see if you can answer it. I did all that work to get to that one statement. The autocovariance matrix has to be positive, send down.
Back in.
So Positive semi-definiteness is a property of a matrix which you can verify in multiple ways. The simplest way is to use eigenvalues. We want the eigenvalues to be positive in magnitude or 0. If that happens, then we are okay. Negative eigenvalues, not good. It will go back to the unit circle, roots lying inside the unit circle instead of being outside. So we can use this condition to verify stationarity. Once again, this is okay if we have a matrix that is sparse, not a big deal. By sparse, I mean a whole lot of zeros, very few numbers. Not a big deal at all. If it is not positive semi-definite, then the series is not going to be stationary. While the process itself is complicated, when we have other elements, we've got to understand that in practice, one would encounter things such as this. I'm going to pick any of these three. Good. So what is the difference between the matrix gamma 3 and the matrix gamma n? The generalized version that I wrote.
There are zeros.
It's a full matrix, right? No zero elements. Every single one of them is some value. Over here, sparse, not sparse. So we've got to check for stationarity, and here things are going to get complicated because as the matrix grows, natural computation will become difficult. What does this mean? If I ask you, well, from here, pick covariance of AT, AT plus 1. AT, AT plus 1. 0.2. Well, I should have simply pushed that 0, 1, my bad. Of course, for any t, this would be the same, right? But easy to understand this way. Covariance of A1, A0, those are constants, they are random variables. What is that value? Point 2. Covariance of A3, A3. Or A2, A2, or 0.5. So, do we consider that the values are symmetric? The matrix is symmetric. So, condition is symmetric, positive, semi-definite. That's what we want for our covariance matrix. This is a case where we might have stationarity if it is positive semi-definite. However, do you believe that our basic fundamental assumption is satisfied, or does it hold true here? Almost.
The assumption being,
What are the basic assumptions that we have with a series?
in terms of error, it's identically distributed, and
Independent, identically distributed, and in other words, AT plus H would be sigma squared A if H is 0 or if the time indices are the same, right? Is that the case here? 0, 1, the covariance is 0.2, but 1, 2, the covariance is 0.2. 2, 0, covariance is 0.1. The variances are not the same. So we might have a serially correlated series, which would also make it non-stationary. Good. This definitely is positive semi-definite. Most likely not. Could it be? Yes. But full matrix, there could be issues. But regardless of whether positive semi-definite or not, this is a case where we are saying the noise components are related to each other. The noise also changes with respect to time. So A0 varies with A1 in that manner. A2 varies with A0 by that value. So our basic assumption for AR and MA is, well, the variations between different time points among the noise components always sigma squared A. No matter, sorry, I take that back. No matter what time point you pick, you would have sigma squared A, but if you did A1, A0, it is 0, A2, A1, 0, A3, A1, 0. That is the case over here. That is our assumption. This more complicated serial correlation. Good. Finance, volatility. Most likely we would see a full or at least partially full matrix. Good. Could it be stationary? Possible. I'm not saying if you encounter something like this, it is going to be non-stationary. It is more likely to be non-stationary than stationary. Good. Why does this matter? Well, the estimations that we do in order to find the psi weights, you know, the ones that we did last class, the class before, we converted AR1 to MA infinity, we went back and forth, invertible. But I mentioned, well, in practice, I don't know what the psi values are. Our objective is to estimate those values using the series that I observed, correct? That plays a significant role in finding those coefficients. Without the autocovariance matrix, you cannot find it. Good. Now, I will do cases where we would go all the way up to 2, right? Which would simply mean take an AR model. What is the order? If I went all the way up to 2, 3, 0, 1, 2. So time 0 is T, 1, 2, right? Order 2. Past that gets really painful. How do we do it in real life? computer. And computers can only work with inverses of matrices sometimes, right? You can't always invert a matrix, but if you know a matrix is positive semi-definite, it is invertible. Good. So all of this needs extra work. For the AR1 case, you would start seeing the feeds pop up here. When you get to AR2, you would start seeing phi1, phi2 pop up right there. So once you have the data, you do the inversion, you can solve for phi1, phi2, etc. Same with the MA model. Is there something else I mention today? I think that is it. Are we clear? In terms of estimation, there are methods such as Yule, Walker, Darwin, Watson, very common algorithms. When I do AR2, we will do the Yule-Walker equations, AR1, AR2, the rest we need the computer answer. Are we clear? Any questions? This positive part, it is related to eigenvalues. But why do we have this condition? Think of the simplest case, variance. Could variance be negative? Variance. Could it be negative? Absolutely not. Could it be zero? Yes, variance between two constants is zero. Positive. Semi-definite. If I say that it can't be zero whatsoever, positive, definite. Does that make sense? So we put positive semi-definite because eigenvalues positive, it could be zero. Why? Only then will this matrix satisfy properties of variance. Every variance matrix, covariance matrix will satisfy that condition. If not, it is not a covariance matrix. Good. Any other questions? If not, we will stop here.